So this is red in maze class. See here, we have given a maze. It's a 4 cross 4 matrix having zeros and ones. Now let's go ahead with creating and calling a method to solve this maze or to find the path to be traversed by the red. So let's call it solve the maze, and the first argument to this method is the maze itself. Now we have to make the red start from somewhere, and the position from where the red starts its journey is the first cell, where the value for both row and the column is 0. So let's pass x and y, and solve the maze is gonna return a boolean. So to accumulate the result, we don't have anything yet. So we need another matrix of same size. Let's take n, which would be equal to the maze dot length, which for this maze is 4. And now let's create another matrix of same dimensions. Let's call it sol, and it's new int n. And after creating it, I'm going to pass this matrix and the n in this method. And let's start the main implementation. So when we implement backtracking problem, first we check for constraints. So the first element is constraints, right? To check the constraints on the current cell, let's create a separate method and let's call it isSafe. And let's pass maze xy. Let's name I and j, replace with x and y. If this is true, then mark the current cell of the solution matrix, which is sol xy, mark it 1. So we will put 1 here in this cell in our solution matrix. Let's tell the program when to include this cell by implementing this isSafe method. So here in this isSafe method, what are the constraints we are going to pass? First condition is that x and y both must be present inside the maze. So x must be greater than or equal to 0 and it should be less than n. And similarly, we have y. Y should be greater than equal to 0 and y must be less than n. And the current cell must be having value 1. So maze xy must be equal to 1. So if this is true, then this isSafe method is going to return true. So when the cell is safe to be included in the path traversed by the red, we're marking it with 1. Now comes recursion. We have two choices. First, we can go in x direction. So let's check if we can go forward in x direction. If solve maze, so here comes the recursion where we are calling the solve the maze method recursively, and let's pass the maze. We're going to go in x direction, so we have to increase the x by 1 and we will keep the y same and then pass the solve matrix and n. So if we can go forward in x direction, we're gonna return true. Otherwise, we can go in y direction. So let's again call solve the maze recursively. It's gonna return boolean, so let's change the return type and now solve the maze, pass the maze, and we'll keep x same and we will increment the y and we will pass the solve matrix and n. So if we can go forward in y direction, we're gonna return true here. But if none of the above movements work, then we have to backtrack. So let's backtrack. How are we gonna backtrack the solution? Let's write the backtracking step. Here we set the value for this current cell with 1. So here we are going to undo our decision. So let's unmark XY cell as part of the solution. And to do that, we just have to overwrite it with 0 and now return false, saying that this current cell cannot be included in the solution. So almost the solution is complete. Now comes the base case. So if we reach to the goal, when we will reach to the goal, when the x will be n minus 1 and y will be n minus 1, because this is the last cell. So here we will update the value for this last cell and we will return true. So these are the preconditions, that x must be n minus 1, y must be n minus 1, and the cell must be having value 1. If this is true, then we will update the last cell of the Sol matrix with 1 and will return true. So this is how we will get the final updated path as the Sol matrix. Let's add the return statement. So if it is not safe to include the current cell, then we are not going to do anything. We will just return false. Now the implementation is complete. Let's go back to our main method, and here let's print the solution matrix. So for first loop is for, let's say, rows. So for I equals to 0 until I is less than n, we're gonna increment the I, and inside this we're going to take another loop for columns j starting from 0 till n, and increment the j, and here we're going to print each element of this Sol matrix, so Sol ij, and we're gonna separate these elements with spaces. So we're gonna put some spaces between these elements and one space after this element, and then one row completes. After that we will change the line, and here it should be print. So this everything we are going to print only when the solve the maze is going to return true. So if solve the maze return true, then print the solution matrix, else print that path not available or no path available. So now this is the complete solution of the red in maze problem. Let's try running it and see what we get. So this is the solution matrix where we have this path from this maze that we initially had. Now let's change this and again run this. This time we have two paths, right? So let's run this. This time the path we get is this one, because first we are taking x, and here x is standing for rows. So if we are going recursively towards x, that is, we're changing rows each time. So that's why this is the solution path. And this is how we can solve the rat in the maze problem using backtracking. Let's meet in next lecture with a different problem.